calculus students, this is the second day of section 5.3. We had covered cosine and sine, sum and difference formulas yesterday, and so we just have tangent left here. And yes, this is a more involved formula, but again, if we were to use it for a few days, we would realize that tangent of u plus v always starts with addition in the numerator. Tangent of u minus v always starts with subtraction in the denominator, or in the numerator. And then we'd go back and see, while it seems kind of weird to have that 1 minus in front of there, we had addition in the numerator, so subtraction in the denominator, and that was for our sum formula. And then when we go to the difference formula, we have subtraction taking center stage on the top in the numerator, and so the opposite of that is addition in the denominator. So again, there's patterns within patterns here, and one of the things I would have liked to have seen the book do was actually go through the proof of those, but that is something we could do because we know that the tangent of theta equals the sine of theta over the cosine of theta. In fact, there are people that just use that as they go through it. And because I do want you to get the feel for how the proof would go so that we absolutely could prove what we need with sine of theta over cosine of theta, that's how I'm going to do this one since they didn't give us the proof itself. So you can see how all of this would work out. So this is kind of the long way to prove this reduction formula. So sine of theta follows that pattern. We're going to need sine, cosine, cosine, sine, and this was subtraction, and sine, cosine, cosine, sine keeps that subtraction. We're going to put theta and 3 pi over 2 in here. And then we'll go down to the denominator, and we need the cosine, and we want to use theta minus 3 pi over 2. So cosine, cosine, sine, sine, but we have to change from a negative to addition. So subtraction becomes addition with cosine. Theta, 3 pi over 2, theta, 3 pi over 2. And hopefully, when you saw the 3 pi over 2 right away, you were thinking about that quadrantal angle right there. So let's see what we get. In the numerator, we have the sine of theta times the cosine of 3 pi over 2. This is the cosine of 3 pi over 2. It's 0. Minus cosine of theta, and then we have the sine of 3 pi over 2, which is a negative 1. In the denominator, cosine of theta and the cosine of 3 pi over 2, which was, of course, 0, plus, and then we have the sine of theta, but that's times the sine of 3 pi over 2, which was negative 1. So in the numerator, we now have minus a negative going on for cosine, so that would be cosine of theta. In the denominator, again, anything times 0 is 0, that's going to disappear. And sine of theta times negative 1 would be negative sine of theta. So cosine of theta over negative sine of theta, and I start thinking, I want this as a single trig function, so I'll put the negative on there, cosine over sine. What is that? Oh, that's cotangent of theta. So that leads us to where we need to be. Again, you could prove this reduction formula with the tangent difference formula right here. Come on, blue. There we go. Once you've seen the proof for it. So like I said, this isn't the proof for tangent theta equals sine of theta over cosine of theta, but it gets so close that I think it gives you a feel for how that formula would work, and it might be one of those things they have you prove in the homework. So example 6 says, let's use it now. You know, we want to use the sum or difference formula to find an exact value for the tangent of 5 pi over 12. So I start thinking, well, that would be 2 pi over 12 plus 3 pi over 12, which would reduce to pi over 6 plus pi over 4. So that would be a good one. But like we talked about yesterday, there are a lot of options here. In fact, you could use subtraction here by 2 pi over 3 minus pi over 4. because over 12 we'd have 8 pi over 12 minus 3 pi over 12, which of course is 5 pi over 12. So different ways to get there. I think most people would probably go after the pi over 6 and the pi over 4 right there. So we grab our formula for the tangent of, I'm going to go ahead and use the addition here, the tangent of u plus v, and we see, all right, we're going to stick with addition in the numerator. So tangent of pi over 6 plus the tangent of pi over 4 divided by, and now we need the subtraction. So addition in the numerator means subtraction in the denominator, minus the tangent of pi over 6 times the tangent of pi over 4. So now I realize I need to know the tangent of 30 degrees and the tangent of 45 degrees. All right, so Smartboard was giving me an issue there. I just went ahead and drew those on there with my 30, 60, 90 and my 45, 45, 90. There was a big pause between when I wrote things and when they actually showed up. So now we need the tangent of pi over 6, which is the tangent of 30 degrees. Opposite over adjacent, 1 over the square root of 3, but we rationalize the denominator, and we get the square root of 3 over 3. And then the tangent of 45 degrees, which is pi over 4, opposite over adjacent is 1. So let's put those in there. Tangent of our 30 degrees was the square root of 3 over 3, plus tangent of pi over 4, which was 1, divided by 1 minus the square root of 3 over 3 times 1 over 1, or just 1 in this case. So now we would definitely want to figure out, well, what exactly is going on here? I mean, we've got fractions inside fractions. So we could go ahead and find a common denominator for our numerator here, and that would be 3. So we'd have 1 written as 3 over 3, and that would give us the square root of 3 plus 3 over 3. And down here on the bottom, same type of thing. We could make this one a 3 over 3, and then we would have 3 minus the square root of 3 over 3, because multiplying by 1 isn't going to do anything for us there. And then finally, when you have a fraction divided by another fraction, you multiply by the reciprocal. So square root of 3 plus 3 over 3 times 3 over 3 minus the square root of 3. And we see that the little 3's, numerator and denominator, I guess I should say the first one's the denominator and then the second one is the numerator, they cancel right out. And we have the square root of 3 plus 3 over 3 minus the square root of 3. Now, the question is, should we leave that? And the answer is, of course, never. We're trying to find these because what we're looking for are perfect answers. That is not a perfect answer. We know we're not supposed to leave radicals in the denominator, so we would multiply the numerator and the denominator by the conjugate. And then we'd see what happens. So go after your denominator first. First times first is going to give us 9. Outside times outside plus inside times inside is going to cancel out because of the sum and difference pattern. So we can go directly to last times last. And we realize, well, that's going to be 9 minus 3. And that's 6. So multiplying by the conjugate there did exactly what it was supposed to do. And now I just have to be careful and use my FOIL for the numerator. So first times first will be 3 square roots of 3. Outside times outside will be plus the square root of 9. Inside times inside will be plus 9. And last times last will be 3 square roots of 3. So I have the square root of 9, which of course is 3, and that will give me 3 plus 9 is 12, and then 3 square roots of 3 plus 3 square roots of 3 is 6 square roots of 3. And then I notice, hey, 6 divides evenly into everything in my numerator, so I'm going to factor out a 6. And that way, once I see the multiplication, I realize I can cancel because canceling is a form of division. So tangent, it involves a little more work, but again, look at that. That's a perfect answer. That is definitely an elegant answer in math. And that's for an angle. We otherwise would have said, hey, we're going to have to use a calculator for this because that was 5 pi over 12. And here it is perfectly. So like I mentioned, there over the years, thousands of years, the goal has been to find as many of these angles as we possibly can with perfect measurements. So those ratios of two sides that we have for sine, cosine, tangent, and the secondary trig functions can be as close to perfect as possible. And that's what we did. So now you can go back and you can finish the rest of the 5-3 homework. Anything that has to do with the tangent, you will be able to do now. Have a great spring break, everybody. Take some time off and relax a little bit. Bye-bye.